Sorry, for a moment I forced to pause the video for some official I left. Anyway, for 200 milliliter sodium hydroxide addition we calculated in data processing part. Remaining 100 milliliter, you remember lastly we said after 200 milliliter addition it ended up to hydroxyl molarity, hydroxyl concentration, and by getting minus logarithm, it led us to POH, and then we said 14 equals pH plus POH. If you plug it to POH place, substitute it here, subtract it from 14, it gives you pH that we claimed it is probably quite close to 8 point something. And then 100 more milliliters left over, since totally we are tending to add 300 milliliters. So once again, for the last 100 milliliter hydroxyl, again, since right now, if we assume this one is titration curve, let's say NaOH addition, 100, 200, and 300. And right now 2, 4, 6, 8, 10, 12, 14. So we said for when still we kept close the stop calc, it was 2.7 after 100 milliliter addition. It was around 4.7 according to the field table we fill blank here. And then 200 milliliter suddenly it went up, so let's say it was somewhere here. So we are going to see what will be pH after 300 milliliters addition. So you see right now acidic part is over. The equivalent part we passed over it, and right now purely we're working in basic area. So you see it is more than 8 point something. So from now on we face a hydroxide lanolene. That's why I'm tending to find out molarity for a hydroxide, and that's it. So let's say hydroxide is 0.05 molar, and we said mole over liter, this time 300 milliliter, that's why number of moles equals 0.015. And last amount of acid we neutralized that was from the last step. So if this one is for hydroxide, last amount of acid was 0.01 number of moles. That's why remaining hydroxyl part equals 0.005 moles. Divided by total volume, which is right now 350 milliliter, is going to give us concentration. Whatever we have here, by getting minus logarithm, once again, it is just for hydroxide, this number of moles. Neither acid nor anything else we have in reactant side, and that's why just we are talking about hydroxyl lanolene. So Px this time equals POH, and again soon after you found out POH, I mean just substitute this value instead of OH, and by getting minus logarithm it gives you POH. And then you say again 14 equals pH plus POH. If you substitute it here, it gives you, by subtracting from the 14, it gives you pH lanolene. According to our calculations in class, it was like 12 point something. It ends up here. This one is your titration curve. It begins from here and ends up to 12 point something. I was wondering what was it. And table is filled theoretically, and all calculations are covered here. Then for conclusion, these mostly these parts were about data processing. Right now I want to say what you have to write for calculations. For calculations, you have to do two jobs. So let's say, conclusion, not conclusion. You've got to do two jobs. The first one, comparison between theoretical results and practical results. Secondly, whether or not our hypothesis is confirmed. So in hypothesis, we said we start from acid, then buffer, and ends up to base. Pretty sure our hypothesis was met, since you saw both theoretically and practically confirmed our hypothesis. But in terms of how qualitatively and how even quantitatively they agree to each other, there are some deviations. So these two goals must be met in conclusion. Comparison. You have a table, a table theoretically, NaOH, addition, pH. You said 0, 100, 200, and 300, and you said 2.7, 4.7, 8 point something, and 12 point something. And you draw titration curve. It was like that one after you graduated for sodium hydroxide and pH. And then, and then practically, we'll see how they agree each other. Practically, you had the same addition, NaOH addition, but for some groups, for example, equivalent point was met in different values. For instance, 0, 100, for either 150 or 175. You have to write your own practical values and then compare your curve with theoretical. Probably pattern will be the same. In a parallel pattern, they're driving, ending up to the base area. That's why it is not quite challenging. Just write your own values, probably for 0, 100, either 150 or 175, 200, and 300. And then once again, for practical, you draw titration curve and you see how they agree each other. You may discuss about some deviations in evaluation part. So in evaluation, pretty sure there are some errors, although generally they agree each other in laboratory as far as I remember. But in some details, probably as I said, equivalent point could be met sooner than the theoretical one. No matter, you may discuss about it, what causes this deviation. For instance, I remember when students told me once that I must have used a clean graduated cylinder, and she was pretty sure right. And different types of error you may discuss in evaluation, either instrumental. So you remember, in practical, I forgot it, guys. You had to say that whilst we were running titration, we used pH meter, and it is quite important since I had a bunch of matters for writing and speaking. That's why I skipped over it, and probably I forgot it. But later on, you've got to discuss about instrumental errors. So our pH meter could be miscalibrated. Personally, since it was demonstration, I could make some mistakes, and also, I mean, personally, I could be not very perfect. That's why personal error is inevitable. Method. In terms of method, probably as far as I remember, even we didn't calibrate pH meter, or the way I ran the titration could be not as perfectly as we expected, and also chemical quality could affect an error. So you may discuss about different types of errors. Particularly, these are going to be a reason for systematic error. And random error, pretty sure we faced some random errors since we didn't carry out experiment in a very standard conditions. That's why random error was met as well. And then you've got to say how we are able to get rid of that. And also, even in terms of different errors, different types of errors, we face constant and proportional as well. Since, for instance, burette, if this one is not clean enough, it causes some errors as well, and you may discuss inconstant and proportion errors. I do not want you to go deeply through the errors, but briefly I expect you to discuss about different types of errors, and also you may say how to get rid of those errors. For instance, instrumentally, you have to miscalibrate pH meter. You have to calibrate pH meter since it is miscalibrated. Self-discipline for personnel helps you, and the method could be compared to the reference. And probably some controlled condition helps to reduce random errors. That's it, thank you, it's over. I'm standing as well. I pull myself over to let you make a screenshot if you need that for a report. Hopefully it helps you. By the way, this part was the second part for weak acid titration. Last video was first part for weak acid titration, and probably in next video I'm intending to upload video for buffer preparation.